So in this lecture 13 we'll be discussing stereochemistry. Stereochemistry is a spatial or an important part of organic chemistry discussion. This is important because most of the enzymes, natural products, contain stereochemistry, or they have different stereoisomers within them. That's actually what would give those biological molecules their specificity, their activity in terms of in our bodies. Enzymes, DNA, RNA would all contain stereoisomeric centers. Therefore, it is very important to study stereoisomerism in the context of biological activity and natural products that are in our bodies and in plants and any of biological important compounds. Medicines, they would have a specific stereoisomerism. One isomer could be a painkiller, maybe the other would not have any activity. That means stereoisomeric compounds are important class of compounds where they have the same constituents, the same chemical property or functional group, but they display, or their three-dimensional display in space is different from one another. They could be mirror images, maybe they will not be mirror images if you have more than one chiral center. Therefore, we study stereoisomers in detail in this next. Stereoisomerism in this video, I will be trying to summarize what stereoisomer compounds would look like. So as a recap, the same molecular formula compounds could be isomers. That means they would be the same molecular formula, we call them isomers. But if they are not the same molecular formula, there is no talk of any kind of isomerism between two compounds. So the first thing, criteria to be an isomer would be to have the same molecular formula. Isomers have the same molecular formula. But the next question would be, are they constituted in the same manner? Connectivity-wise, are they the same? For example, if it is no, you would generate different compounds. For example, this is a molecular formula of C2H6O. This is the same C2H6O. That means the same molecular formula, but constitutionally they are different. Therefore, they are constitutional isomers. Constitutional isomers are compound pairs, compounds that have the same molecular formula, but they don't have the same functional group, they don't have the same chemical property, they don't have the same physical property. This is a difference like two functional groups. This is an alcohol, ethanol, this is a dimethyl ether. Constitutional isomers do not display the same physical and chemical property because their constituency, that means carbon here, you see here carbon, oxygen. So they are constituted differently. They are constitutional isomers. But if the constitution is the same sequence of how they are bonded, they would qualify as stereoisomers. But within stereoisomers, you have also two kind of classes. That means enantiomers and diastereomers. So in enantiomers, for example, in terms of how they are, if you just take an example of my two hands as mirror images to one another, those are stereoisomers. The reason being, there is a plane mirror that reflects one over the other. They have the same constituents, 5 fingers. They are equidistant from the plane of the mirror. Therefore, they are mirror images to one another. But if you just look at them and try to superimpose one over the other, if you are trying to superimpose one over the other, they will not be superimposable. Therefore, compounds that are mirror images but cannot be superimposed in their own mirror image, they would be enantiomers. So there is a designation for mirror images. If they have only one chiral center, we will discuss that, what chiral center is. they could be designated as R enantiomer and S enantiomer. But when you have more than one chiral center within a compound, for example, 2 chiral centers, which can be designated as R or S, RS, just this is an example for the 2 centers, you would have also SS possibility, SR, RR, all of the combinations. So you would have 4 diastereomers are possible when you have 2 chiral centers. But diastereomers are compounds which have chiral centers in them, but they are not mirror image. For example, the relationship between an RS and SS compound is diastereomeric relationship, meaning that RS is not the mirror image of SS, but each one of them have a chiral center. So the mirror image would have been, for them to be enantiomers, RS, if the other compound was SR, that's a mirror image, they would qualify as enantiomers. So for diastereomers, they have chiral centers, more than one chiral center, but they are not mirror image to one another. RS is not a mirror image of SS, but the mirror image of RS would have been SR. SR would have been a mirror image of RS, therefore it would be another enantiomeric pair. So we'll be diving in detail with specific examples in this chapter, where we discuss mostly stereoisomerism. In previous chapters, we have seen different constitutional isomers. They are physically different, chemically different. Here, enantiomers are chemically the same, the functional groups are the same, but the only difference is they would have different physical property. Specifically, when it comes to their interaction with light, they would be different. That's how we measure actually the degree of polarity of these compounds called stereoisomers.